What up, guys? Welcome back to the channel. Eric here, back at it with another breakdown. Here we go, guys. The more passages you do, the more you develop that skill of reading these, complicated research passages that are kind of annoying, not gonna lie. Okay, the better you get that skill at making these easier, the better you're gonna do with the MCAT. The higher those, big jumps, you're gonna go from like a 124 to like a 129, 130. You're gonna hit those. Okay, just do what I do in these passages. Okay, I make it very easy. If you want those big jumps, you got to make this MCAT easy. You got to make it easy. Okay, and it is easy. It's a lot, but it is easy. And I show you guys exactly how to do that. So we're gonna be breaking down another CP Chem / Phys passage. Okay, this is from the Blueprint exam. This is the free FL they give you guys. I'm gonna go ahead and break this down. All right, I'm gonna show you guys exactly how to answer the question, how to pick the best answer choice, blah, 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 highlight everything that you guys need, make it become easy for you guys. So before I break it down, guys, you have to do it first. All right, so read through the passage first. I'm gonna go through these questions, so write down your answers that you chose and why you chose it. And then click on this video and hear me break it down and compare and be like, hey, I messed up because of here, or I did good and I got it right because of X, Y, Z, okay? I want you guys to get in the test maker's head. The more you get in that I almost cursed again. The more you get in that test maker's head, the better you're going to do, okay? Because it's very predictable. They're very predictable, all right? So I'm going to scroll down here, guys. Pause it whenever you need to, all right? Read through that passage. Here's the first question. Pause it whenever you need to. Here's the next question. Okay. And that's it. All right. So pause it whenever you need to, guys. Write down your answers. Let's see how many you got right. I'm going to break it down for you right now. Pay attention. It's going to change your MCAT score. All right. Here we go. A key modulator of action potential firing is the hyperpolarization activated cyclic nucleotide gated HCN ion channel. Wow. Thanks for that mouthful. These channels are permeable to both sodium and potassium, the HCN current. The HCN current, IH, is found in neurons under hyperpolarization of the cell membrane. IH is proportional to the frequency of firing of action potentials. Oh boy. I know a lot of students do not like electrophysiology. All right. So what do we got here? IH. All right. Every time I'm given a variable, I like to kind of highlight it. It kind of puts a reminder in my head of what the heck is going on. Okay. So HCN current is IH. It's found in neurons under hyperpolarization of the cell membrane. Hyperpolarization, guys. Okay. IH is proportional to the frequency of firing of action potentials. That makes sense here. All right. If you guys are going through a passage and you're encountering a weakness of yours, okay, for me, electrophys is my weakness. Okay, some people have different weaknesses. I think that beta oxidation, fatty acid synthesis, gluconeogenesis, regulation of all that, I think that's pretty easy. Some students think it's hard. Okay, this is my weakness here. If I'm encountering my weakness, I'm going to slow down. I'm going to slow down and make sure I understand every sentence of this passage. Okay, I'm going to take a deep breath, relax myself, slow down, and get through this. Okay. Neurologists wish to determine if a new drug, compound X, is able to block IH and reduce neuropathic pain, providing significant analgesic effects to those with pain. Okay, cool. Let's see if it works. All right, and these are the drugs. Compound X's effect on neuronal firing was first compared to lidocaine, a known sodium channel inhibitor. Ganglion cells were treated with 3 different concentrations of compound X. All right. Sodium current was isolated and then recorded using patch clamping. Figure 2 shows the results of these recordings. Okay, so they're trying to see the firing, how they compares to lidocaine when they use compound X here. Okay, and I'm not going to go ahead and look at these figures yet. Only when the question asks for it, I look at these figures. All right. You could read this. You could read this part. That's fine. All right, so sodium current in ganglion neurons treated with compound X. traces were recorded in the presence and absence of different concentrations of compound X. All right, this makes sense. All right, if I have smaller concentrations, higher concentrations, what happens to the firing potential? Does it get hyperpolarized? Does it get depolarized? What happens? Okay. To test if compound X was indeed also a blocker of HCN channel currents. All right, so simple but effective sentence here. All right. They want to confirm the results that it is an HCN channel blocker. Okay. The effect of the drug on HCN currents in ganglion cell neurons was recorded. HCN channel whole cell current in neurons was induced by giving a membrane potential step from a holding potential of negative 60 millivolts step to negative 140 millivolts steps for 700 milliseconds, then back to okay. It's okay, guys, if you read something and you're like, huh? All right, that's fine. Because I read this and I'm like, well, what the fuck is going on? Okay, that's fine. So if that happens, you don't want to waste time. I give you the permission to reread the sentence once only. That's it. And slow down. HCN channel whole cell current in neurons was induced by giving a membrane potential step from a holding potential of negative 60 millivolts step to negative 140 millivolts for 700 milliseconds and then back to okay. So what they did here is they hyperpolarized it. So negative 60 to negative 140, you're hyperpolarizing the potential. Okay. And they did that for a duration of 700 milliseconds. And then went back to negative 70. So it repolarized. Okay. It didn't repolarize. It depolarized. Okay. My fault. It depolarized back to negative 70 millivolts. Okay. Why are they hyperpolarizing it? Well, remember, okay, it's the neurons is under hyperpolarization of the cell membrane. That's when it's found, when it's hyperpolarized. So it makes sense that that's why they're going to hyperpolarize the cell membrane. Okay, they want to see results. They want to compare. All right. The best way you compare your results is to kind of stimulate what's going on in the body. You know, what's going on in this protein, this channel. All right. Solutions of 5 milliliters each were prepared with differing amounts of compound X. This kind of struck out at me. Okay, especially the 5 milliliters part, because they told me an exact concentration. Okay, this struck out at me. So I'm going to highlight this. Figure 3 shows the concentration effect of compound X on HCN currents in neurons. Figure 3, inhibition of HCN currents by addition of compound X. Okay. So this is the current, and they want to see. All right, that's annoying of them. They just put log X. They could have made this a little more specific. They could have helped us out a little more, but that's fine. All right. This passage, I would say it's on the more difficult one. Okay. For me personally, I think it's on the more difficult one. Okay. Delta I over IH, that's the current. That's a change in current. And they want to see what the change in current is when they add this compound X with different concentrations. Okay. Now, do I feel amazing? Am I doing backflips off my chair right now because I understand everything in this passage? No. Okay. And it's fine. It's okay if I don't feel 1,000% comfortable. But the thing is that I'm used to not being 100% comfortable with these passages. And that's why I get the scores I get. Okay. I understand that I'm not going to understand everything. And that's fine. I'm going to have trust and confidence in my abilities of how I studied and how I take these passages tests to get the answer that's right. Okay. Confidence, guys. You got to be a confident bitch when you fucking take these fucking MCAT questions. All right. Compound X and lidocaine can be separated using either abstraction because. Okay. This is content review here. You're going to have the organic layer and the water layer. Okay. Ether dissolves the organic layer. So one of them is going to be lipophilic and hydrophilic. All right. If I look at these, structure of lidocaine left and compound X right. All right. Left, I would say, is pretty lipophilic. It's hydrophobic here. Okay. I don't really see any charged ions here. It's kind of symmetrical a little bit here, but it's more of the lipophilic. All right. Now look at compound X on the right here. I do see some charges here. I see a chlorine minus and plus here. That 100%. If you see that plus here, okay, or some charges, you already know that it's going to be hydrophilic. All right. So lidocaine is lipophilic while compound X is hydrophilic. That's lidocaine. That's compound X. Yes, that's correct. Compound X is lipophilic while lidocaine is hydrophilic. Again, compound X is lipophilic, correct? While lidocaine is hydrophilic. Wrong. Okay. Lidocaine is lipophobic. Oh my God. All right. My bad. Let me go back to my words, okay? Compound X is lipophilic. All right. And while lidocaine is hydrophilic. All right. This is how they're trying to trick you guys. Okay. Lipophilic, hydrophilic, hydrophobic, lipophobic. All right. Hydrophobic is the same as lipophilic. All right. Remember that. So don't get confused here. Both molecules are hydrophobic with only nonpolar groups. Wrong. Okay. That is wrong. This is not hydrophobic. Lidocaine is hydrophilic while compound X is hydrophobic. Compound X is not hydrophobic. All right. The answer is A. Comment down below if you guys found that a little tricky. Okay. I'm glad that they asked this because a lot of students think the same, like lipophilic means the same as hydrophilic. All right. It's not the same. It's different. Based on the observed effects, what is the minimum dose of compound X required to reduce the HCN current to half the normal current? Okay. Observed effects. This is telling me I have to go to some experimental results. All right. This one, they tested the kind of the hyperpolarization and the presence of compound X there in regards to the hyperpolarization here. Okay. What happens? Does it get depolarized, get hyperpolarized? Does that get blocked here? Here they talk about the current here in figure 3. So I'm going to jump to figure 3 here. And I look at the X and Y axes. Okay. The X is the concentration of compound X. Okay. Log X. They put in a log form here. And the Y axis, delta I over IH max. Well, I know IH is the current, the HCN channel current. And delta means change in. So I guess it means the change in current. All right, the change in current when we add specific concentrations of compound X here. Okay, so here is the data here. It goes, and goes up. All right, and they want to see to reduce the current to half. All right, 7 is not reducing in half. 6 is not reducing in half. 5 is like up here. It matches with, and I could say that that's half. Here's 5. This is half of the data, and this is the other half of the data. So I like 5. 4 is way too high. That's like 100%. Okay, so 5 is a good number here. -5 is the concentration. All right, log of -5 is the concentration that's needed to reduce the HCN current to half. Now, this is concentration. Concentration is measured in molarity. All right, they give us the answers in moles. So we're going to have to convert from molarity to moles. All right, so I'm going to have to do the whiteboard here. I need the whiteboard here. Let's see. This one, right? I think this is it. Oh, no, that's not it. I need the online whiteboard. Is this one it? Oh my gosh, give me a whiteboard. What's going on here? Technical difficulty, guys. I think this is it. All right, cool. We got the whiteboard here. All right, sorry about that. So we have to go from -5, log of -5, molarity, to, what do we got to go to? To moles. To moles. Okay. Log of -5 is 10 to the -5. You guys should know that. And molarity, I don't like to use molarity like that. I like to put it, this is what I like to do. I like to change it to moles per liter because that's what molarity is. All right, molarity is moles per liter. All right, and I do this because when I go into the dimensional analysis stuff, it just makes it a whole lot easier. All right, and if I want to get from molarity to moles, I'm going to have to cancel out liters. Okay, so I need a liter to be up here. I need a volume to be up here. So if I do that, then I just get moles. All right. So they gave us that the solution, okay, here. Solutions of 5 milliliters each were prepared with differing amounts of compound X. Figure 3 shows the concentration effect of compound X on HCN currents in neurons. So 5 milliliters were prepared from this. Okay, so it's 5 milliliters. See what the data is. 5 milliliters here, 5 milliliters here, 5 milliliters here, 5 milliliters here. All right. So we're going to use 5 milliliters. Now, 5 milliliters is equal to 5 times 10 to the negative 3 liters. Okay, milli is equal to 10 to the negative 3. So when we multiply this, what are we going to get? We're going to get, liters are going to cancel out, and we're just going to get moles here. So we're going to get 5 times 10. All right, when you're multiplying exponents like this, you just combine them. That's it. So 5 times 10, combine negative 5 and negative 3, you get negative 8 moles. Okay, 5 times 10 to negative 8 moles. And, okay, they wanted micromoles. In order to go from moles to micromoles, you know micro is 1 times 10 to the negative 6. So you're going to divide 5 times 10 to the negative 8 divided by 1 times 10 to the negative 6 to get micromoles. All right, and that's going to be 5 times 10 to the negative 2. Okay, 5 times 10 to the negative 2 micromoles. That is the answer. All right. Is there anything else I want to say about this? Let's see. Yeah, okay, you had to use the volume here. You had to use the volume here. They were looking for moles. All right. How many chiral carbons are present in compound X? Let's go to compound X. Okay, what we got here? Remember, chiral carbons need to be bonded to 4 different substituents. Anything in a ring here, like this benzene ring, none of those are chiral. Okay, like this carbon is bonded to 1, 2, let's say a hydrogen here, that's 3. Those are the 4 bonds of that carbon. Okay, it's not bonded to 4 different things. It's bonded to 3 different things with 4 bonds total. Okay, I'm going to say that again so it makes a little more sense for you guys. It needs to be bonded to 4 different things. All right, here's what this carbon is bonded to. It's bonded to this carbon here. It's bonded to another carbon here. And it's bonded to a hydrogen over here. It's bonded to 3 different things. In order for it to be chiral, it needs to be bonded to 4 different things. Therefore, all these carbons are not chiral. This carbon is not chiral. This carbon is not chiral. This carbon is not chiral. Or achiral, I'm sorry. It's the correct grammar, achiral. This is achiral. This is achiral. This is achiral. This is achiral. Achiral, achiral. They're all achiral. There's no chiral carbons on this compound. Answer is 0. How many grams of compound X, molecular weight 292.81 grams per mole, are required to create a 1.5 molarity solution of the mixture used to test HCN current as shown in figure 3? Wow. Wow. Okay. How many grams? All right. They want the grams here. They want the grams. All right. I'm going to have to use the whiteboard for this, guys, because this could be a little confusing for you guys. How do I? Okay. Let's go over here. Let's get the drawing out. This is what they're asking, guys. Okay. They want, also, don't forget. All right. Where is it? Remember, these solutions are from 5 milliliters. Okay. 5 milliliter. That's the volume. All right. They want 5 milliliters of a 1.5 molarity solution. And they want to know how many grams to make a 5 milliliter amount of a 1.5 molarity solution. All right, I'm going to write this out because that could seem a little confusing. Okay, so this is what they want: 5 milliliters of a 1.5 molarity solution. Okay, so think of it like this, guys. This is a beaker here. All right, and it has a solution. Let's say it's a solution of, I don't know, acetic acid or something like that. Well, that's actually compound X, okay, compound X. So this is a 1.5 molarity solution of compound X. They want to know, they want 5 milliliters of this solution here. So let's say we had like a spoon here. This is a spoon, all right? This is a spoon. This spoon is gonna go in here and scoop out 5 milliliters of this solution, okay? Now that we have that spoon filled with 5 milliliters of this solution, okay, we wanna see how many grams of compound X was required to make that 5 milliliters of the 1.5 molarity solution. All right, does that make sense for you guys? Let me know in the comments below. Okay, so how do we do this? How do we find the grams needed to make 5 milliliters of a 1.5 molarity solution? Dimensional analysis, baby. Dimensional analysis, okay? So 1.5 molarity. I don't like to use molarity. I like to use moles per liter. Okay, how do I move over here? Okay, we have 5 milliliters. We want 5 milliliters of that 1.5 molarity solution. So we're going to put 5 milliliters here. All right, I don't want to work with milli like that. I'd rather just use 5 times 10 to the negative 3. That's a little easier. So how do I erase? Okay. So instead of 5 milliliters written like that, I'm going to write 5 times 10 to the negative 3 liters. So we get liters and liters here. All right, if we do this, we cancel out liters and we get moles. We get moles. All right, so let's do this right now. So 1.5 times 5 times 10 to the negative 3. This is going to be 7.5 times 10 to the negative 3 moles. Okay. Now, what is a mole? Mole is equal to mass over molar mass. All right. They give us the molar mass of compound X. They gave us it, remember? 292.81 grams per mole. I'm going to use 300. I'm going to round this to 300 so it's easier. Okay. So I'm going to, this is equal to 300 grams per mole. Make sure you guys pay attention to the units always. Units always got to cancel out. Grams per mole. All right. So 7.5 times 10 to the negative 3 moles. We know it's going to be equal to mass over molar mass. And we know the molar mass is 300 grams per mole. So what are we going to do? We're going to find the mass. All right. So 300 times 7.5 times 10 to the negative 3 is going to give us the mass. All right. So let's do that right now. 7.5 times 10 to the negative 3. All right, times 300 grams. I'm going to put in scientific notation. So 3 times 10 to the second. All right. And if you're multiplying these, you just combine this exponent and this exponent. All right. So it's going to be 10 to the negative 1. And then we multiply 7.5 times 3. To do this mentally quick, 3 times 7 is 21. This is how I do it. Plus 0.5 times 3 is 1.5, and that's equal to 22.5 times 10 to the negative 1. I go slow for you guys. Grams. Okay. Now, I don't like how this looks, so we'll fix it up. We move to the left here. 2.25 times 10. What happens to this number? Lars. Okay, Lars is the mnemonic I always like to use. I move to the left here, and because I move to the left, I'm going to add 1. Negative 1 plus 1 is 0, so this can just be canceled out as 1. So the answer is 2.25 grams. Bam! Damn, that was a long time. Okay. 2.25 is closest to 2 here, so I'm going to go with C there. All right, let me sip of my water. Okay, let's keep going. What alteration to an HCN channel will reduce the transport of K plus in favor of sodium transport? All right. What's different between potassium and sodium? The difference is the size. All right, they're both positive one charge, but the size is different. Which one's bigger? I think potassium is. Let's see. Oh yeah, potassium is bigger than sodium. Okay. So we're going to use that to separate these two, or reduce the transport of one over the other. Increase the diameter of the channel by adding amino acids. Okay. If we increase the diameter, we're going to favor both sodium and potassium. Okay, they're both going to go through if we increase it. If we decrease the diameter, we're going to allow just sodium to go through and not potassium. Okay? So if we do that, just let sodium go through and not potassium, we're reducing the transport of potassium in favor of sodium. Okay? So the answer is B there. And then replace the serine groups, but I don't see why that would help at all. I mean, you're not even changing the charge here. Yeah, I don't see why that would help at all. So B is the answer for that one. Yeah, and that's it, guys. Breakdown done. I'll see you guys in the next video. Make sure to go ahead if you're interested in working one-on-one with me inside MCAT University. Go ahead, go to the comment section below, click on the link, book an interview session, and we'll see if we're a good fit for each other, and we'll see if you're a good fit for MCAT University. I will make sure that you hit your target score. I've done it plenty of times with premeds, and I guarantee it. I guarantee you'll do that. All right, so be aware of the next breakdown, and I'll see you guys in the next video.